Now let's talk about irreversibility and Gouy Stodola theorem. Okay. Now in this, let's first of all understand what is irreversibility. Now if you look at the actual work done by a system, okay, let us say the actual work done by the system is W. This is always less than the idealized reversible work. Okay, so it is always less than the idealized reversible work, and that is the maximum work that can be taken out of a system. Okay, so this is true, right? And the difference between between the quantities of these two works is equal to the irreversibility of the process. So I can write down that irreversibility, that is denoted by capital I, this is equal to W max minus W. Right? W max is also known as the idealized reversible work, and W is the actual work done by the system. And this is also known as the degradation or dissipation. So this is also written as degradation, okay, or dissipation. Alright, so let's move forward now. So let's analyze the irreversibility for two things. The first case, let us put it as case number A. Let's apply this for a non-flow process. And that is between the equilibrium state when the system exchanges heat only with the environment. So non-flow process means a closed system. Alright, so if you remember that expression, the value of I is equal to W max minus W. So the W max for a closed system has to be written over here, for a closed system minus the actual work done. So this would be equal to, if you remember it, it will be U1 minus U2, is right, minus T naught into S1 minus S2. So this is the maximum work that can be taken out of a closed system, minus the actual work done is U1 minus U2 plus Q. Alright, so this is the expression that we are looking for. So this is the maximum work, and this is the work done by the actual system, or actual work done. Alright, so let's resolve it a bit further. I can cancel off this and this completely, and I would be left with T naught into S2 minus S1 minus Q. Alright, and if you look at this, this is T naught into delta S for a system minus T naught into delta S for a surrounding. Okay, so because now this is not plus, this would be minus, because if you apply the first law, this has to be minus, so this becomes plus. Okay, so you can take on T naught as common, and you would have delta S system plus delta S surroundings, and this is equal to T naught into delta S of universe. Okay, now the value of delta S universe is always greater than or equal to 0. So this means that for a non-flow process, the irreversibility is always positive or equal to 0. Right. Now let's take the case of a steady flow process. So if we take a steady flow process, and if you remember the maximum work done in a steady flow process, now it consisted of a function known as the Keenan function. Alright, so if you remember that expression, so this becomes I is equal to W max minus W. This is equal to this will be equal to B1 plus M V1 square by 2 plus M into Z into Z1, M into G into Z1 minus, for the second state, B2 plus mv2 square by 2 plus m into g into z2. So this is for the maximum work done. Let's look at the actual work done. So that will be equal to minus h1 plus mv1 square by 2 plus mgz1 minus, you'll have h2 plus mv2 square by 2 plus mg into z2. Alright, now if you look at this thing, this is nothing but your Keenan functions. So these are your Keenan functions. The value of Keenan function, that is b, is equal to h minus t naught s, isn't it? So let's put this value at b1 and b2. So similarly, you can straight away strike off the mv squares by 2 and the mgz's. So you are just left with b1 minus b2 minus h1 plus h2. So this is all that you are left with. Okay, so let's put the values of b1 and b2. This is equal to h1 minus t naught s1 minus h2, and it will become plus t naught s1, t naught s2. Okay, minus h1 plus h2. So now I can strike off h1, h1, h2, h2, and this is left with t naught into s2 minus s1. And there's one more value left, which is plus q over here. You will have to write plus q to complete the steady flow energy equation application. So this will be minus q over here. Alright, so minus q. Now if you look at this, this is nothing but delta S of a system, same thing as above. So T naught into delta S for a system minus T naught. Okay, now this is minus Q, so this will be something done on the surroundings. So this becomes plus, so T naught into delta S surroundings, so this becomes T naught into delta S universe, and this is again is positive or equal to 0. Alright, so this would stay plus only if you look at the analysis, because this is plus. Okay, so yeah, this would stay plus only. So this is how you get this value. So this means the irreversibility for a steady flow process is also a positive value. This means that for both flow and non-flow processes, alright, the expression, that is T naught delta S system plus T naught delta S surroundings, it represents an increase in the unavailable energy, that is the dissipation or the degradation. Let's write it down. So for both the processes, this it represents the increase in unavailable energy, or you can say this is also known as energy. So available energy is called exergy and unavailable energy is called energy. So these two terms are very important for you to remember. Now after understanding the steady flow process and the non-flow process and the associated increase of the unavailable energy in these two processes, now let us define the Gouy Stodola theorem and what this theorem is all about. Gouy Stodola theorem. Now it states that the rate of loss of available energy, okay, so let's write it down. So it defines, or it states that the rate of loss of available energy or exergy, alright, in a process is proportional to the rate of entropy generation. Is proportional to the rate of entropy generation. So this is what your Gouy Stodola theorem is. Okay, so if you write down the irreversibility, so irreversibility is nothing but the work that is lost, isn't it? So this is W lost. Now, or the rate of work loss, I would say, this is equal to T naught into the rate of entropy increase in the universe, and this is equal to T naught into S gen, that is the entropy generation rate in the process. So this is the whole theorem is all about. So this is known as the Gouy Stodola equation. So this is Gouy Stodola equation. Alright, and this is a thermodynamically efficient process, or you can say a thermodynamically efficient process would involve minimum exergy loss with minimum rate of entropy generation. So that is the last takeaway from this particular lecture. So a thermodynamically efficient process, alright, this means that the exergy loss is minimum, and the rate of entropy generation is also minimum. Alright, so this is the last point that you should remember. Now, this is all that we have to understand in the Gouy Stodola theorem, and the basic concept was this Gouy Stodola equation. So I hope you understood it, you will remember it. And now in the next video, let's look at the application of the Gouy Stodola equation.